right, so we have a physics problem left to do, and then we need to do just a tiny little bit after that. So probably about, I don't know, 2 or 3 more boards worth here. Here's our problem. A hot air balloon rising at a rate of 12 feet per second is at a height of 80 feet above the ground when a package is dropped. How long does it take the package to hit the ground? So our goal here is a position problem, right? We want to know when its position is 0 right on the ground. So I drew a picture. You can see I marked that it's 80 feet up. Here's my wonderful hot air balloon. It's rising at 12 feet per second, so that's its initial velocity. And now this package is going to be dropped. So a couple of important things here. At the instant the package is dropped, it's still going up at 12 feet per second, right? You're holding it, you're holding it, you're holding it. At the instant you drop it, it's still going up at 12 feet per second. So yes, even though it's slightly counterintuitive, when you let go of that package for just a tiny little bit of time, it keeps going up before it goes down. Anyway, so that negative 32 feet per second squared, that's the acceleration due to gravity. And so acceleration is the derivative of velocity, so I labeled it as dv dt. Now importantly, we have things going in different directions. The balloon is going up, the package is going to go down. So I called up positive and down negative. We need those signs to be in the right order. All right, so I started with dv dt equals to negative 32. Remember, I need a position function. So I took the I took the antiderivative of the negative 32, which is just negative 32t plus c, and that's my velocity function. But then since I know its initial velocity, if I plug in 0 for t, the velocity has to be 12, which gives me that constant has to be 12 here. And so my velocity function is actually negative 32t plus 12. And so then now I'm going to erase the problem and put the rest of it, of what I need over there. But we're just going to continue on. We have our velocity function. We need to get back to the position function so that then we can solve and figure out when it hits the ground. So let's get that on the board. Okay, so now to finish up this little physics problem, we need the position function. So I took the antiderivative of my velocity function, which raises the power on the t here to a square. Remember, then you divide the negative 32 by that 2 that we used for the exponent to get negative 16. A t shows up on this 12 down here, so we get a 12t, and then our arbitrary constant. That's not completely arbitrary. We know how high this balloon is at t equals 0. So if you plug in 0 for t, the height has to be 80, which gives us that constant is 80. So our position function then is negative 16t squared plus 12t plus 80. We need it to hit the ground, so now I put in 0 for my height. This is a quadratic. I used the quadratic formula to solve this, but you'll notice I left out all the work. So I'm going to leave that for you. Go ahead and use the quadratic formula on this mess. If you do, you get t is equal to 3 plus or minus the square root of 329 all over 8, which is a mess. Importantly here, the package can't hit the ground before it's dropped, so any negative values of t are utterly meaningless. So I actually just threw away that minus 1 because 3 minus the square root of 329 is a negative number. Can't have that. So if you plug that into your calculator, you get that the time is about 2.6 seconds. All right, so we have one more thing to put on the board. It's going to take me 2 boards probably to do it. But one more big thing to cover. It's very, very important. So stick around and finish this video. Okay, so I will need one more board after this one. But our last big idea here is really something we've already done. We're just going to give it a name. Definition. The collection of all antiderivatives of the function f is called the indefinite integral of the function f with respect to x. So that WRT is with respect to x. And we write it as this funny looking s symbol, f of x dx. So we've already done antiderivatives. Wonderful, and it's going to be super fun. But basically, this is the second big part of calculus. Calculus can be thought of as derivatives and integrals. We've already done derivatives. We're just going to start in on integration here. We'll see more integration in chapter 5, and if you take Calc 2, you'll get a whole lot more integration. All kinds of crazy stuff. So a couple points on the notation here. This funny little s is called the integral sign. Little f here, the f of x, is my integrand, the thing being integrated. And the dx at the end tells me that x is the variable of integration. That is usually just pretty straightforward, but eventually you can do multivariable calculus, and then the dx really matters because you gotta know which one you're doing. All right, so I have one example that I just couldn't fit on this board. I'll put it on the next board, but basically this is taking antiderivatives, which means don't forget your c's. All right, let's get it on the board. Okay, so our integral that we're going to find, our indefinite integral, because there are definite integrals, our indefinite integral that we're going to find is for x squared plus 7x minus 5 dx. Now, good news, we learned with antiderivatives that you can split them up across addition and subtraction, so I can do the same thing here and basically consider each of those to be their own little piece. So what do we get? Well, x squared goes back to being a cube. Remember, I need to divide my coefficient by that exponent. So 1 divided by the exponent of 3 gives me a third there. So I have 1/3 x cubed. Same thing with the second term. I had 7x, becomes x squared, and we divide the 7 by that 2 to get 7 halves. So we're dividing those exponents, or by the exponents. My minus 5, it's going to have an x now, right? This is like x to the 0, so it goes back to being x to the first. Technically, we're dividing that by 1, but that doesn't change anything. And then don't forget the c at the end. That is a super common mistake. These are indefinite integrals. You get a whole family of functions out of these. Depending on what that c is, they will all work, but we need the arbitrary c at the end here. Otherwise, it's not a complete answer. If you leave the c off, I will be forced to take a point off on your test. You won't like that very much, so put it on there. Anyway, so that is antiderivatives. There will be more fun to be had in Chapter 5 when we take a much bigger look at this thing called integration. So feel free to come back, and it'll be fun. Thanks. Bye.